So thank you for coming. Thank you very much. I guess most of you probably have already heard of what is called open source hardware, which is supposed to be the transposition of the principle of free software into hardware. That is the freedom to distribute copies of the hardware, to modify, to study. Well, I guess you know it. But there are lots. Sorry. Yeah, sure. So, but there are lots of types of open source hardware. There are lots of projects which call themselves open source hardware, and there are two varying. They do anything. They call basically anything open source hardware. And for me, there are three categories of open source hardware projects. The first category is openly licensed development kits from chip makers. Well, I guess you have heard of the BeagleBoard, for example. It's pretty popular. It's a single board computer, which has more or less the power of a laptop, a small laptop, into this form factor. Well, they call themselves an open source friendly, open source hardware project, but basically it's just a development board for the OMAP system on chip from Texas Instruments. You can see here you have this big OMAP chip in the middle. That's the OMAP processor, and basically everything that this board does is done by the OMAP chip. All the rest is just a power supply, a small transceiver here for HDMI, nothing really complicated, and just other simple circuits, but really they don't match at any level the complexity of what is inside the Texas Instruments OMAP chip. Another example is the Mbed from ARM. It's just like an Arduino. I guess everyone knows Arduino here, but it's just smaller, and instead of the AVR processor, they use, I think it's an LPC microcontroller similar to the one on the badge. But on each project, there are nothing really new, in fact, because they're made by companies who sell chips. Chips are actually usually proprietary. A good example is the OMAP, where I think you have enough binary blobs from some features of the chip. And it's nothing really new for openness, because these people just want to sell chips. They don't care about development kits. They don't care about the rest. And actually, when you take one of those kits from such a chip vendor, and you adapt on it, you study it, you reproduce it, they're quite happy because you end up with another product with their chip in it. That's what their reference designs are for. So, well, it's just nothing really new. It's just some little talking about open source hardware, but nothing really new there. Something which is more interesting is the community-developed devices for hobbyists. The best example is the Arduino. I guess that everyone knows. Just a small board, very simple board with an AVR and some USB interface chips to make programming very easy on this board. Another well-known project is the RepRap, the 3D printer. Oh, did it move or something? Better now? Yeah. You think I should take it? Okay. So another very good example is yeah, better now. Another good example of this category of open source hardware devices is the RepRap, the 3D printer. It's also very popular, just like the Arduino. And these projects are more interesting to me than just the development kit from chip makers, because they are a grassroots movement. They are made by hackers and for hackers, which leads to more potential for open innovation. For example, the Arduino is very good in this respect. They recently were using a USB interface chip, the FTDE chip, which converted between USB and serial. And they recently replaced that with a second AVR chip with a more open USB stack on it. And this enables, first, it's more, they get more of the layers of the product which are open, and this yields to actual uses of that were not possible with the FTDI chip before, such as, for example, with this type of Arduino, you can make it recognize as any USB peripheral, like a USB keyboard or anything, basically. But the problem with these devices is people don't really want to spend a lot on such gadgets. And at the same time, they're not produced in huge volumes. And if you want to make a high-tech product with a cheap price, you have to make huge volumes. I mean, the Arduino sold like 250,000 parts, something like that. But for a typical OMAP or AVR product, it's more like dozens of millions when you go to the hardware industry. And the only way they can make the Arduino or the project affordable is I have no choice but use low technology for some community-developed devices for hobbyists. So this brings me to the third category of open source hardware products, which are just like normal electronics devices, but the company which produces them simply uses open source practice. They would release their design files under the GPL, they will accept external contributions, well, everything that companies do with Linux, for example. And the first example of such a project is the OpenMoko. It was really an excellent project. I mean, they wanted to replace the mobile phone, the closed proprietary mobile phones, with a completely free software stack and hopefully hardware. Well, everything didn't work, unfortunately, but I think the idea was excellent. Another the project now is what I'm going to talk more about now is the milkymist one. So the milkymist one is that's the box we have made, and when you open it, you get this central unit. And what is it? It is actually a video synthesizer which take a camera input. Oops. So it takes a camera input. You can film someone, you can film a performer, you can find objects, you can find basically everything. You can film basically everything, and it goes into the milkymist device here, gets synthesized into whatever psychedelic effect you can imagine. Actually, the complete thing is programmable, and you can project them there, and you can interact with as many interfaces as you want, like MIDI, DMX, USB, well, basically all that people in stage use. So who would use such a device? Well, basically VJs. VJs are people, it's a short for video jockey. It's someone who, during a concert or other event, projects some short clips of video which are in synchronization with the music. It's clubs and concert venues who would like to use it like some small ambient device, small music band who don't really want to have a we don't really have someone to do the VJing and would like some easy to set up system. And know what I'm here for, hackers would like to play with advanced digital technology. Because this device is also produced in quite small volumes, but contrary to devices for hobbyists, it's I mean, I can charge, the price can be higher, so I can make any type of high-tech procedure I wanted basically into it. And it stays competitive even with the small volume we have, because the price of professional video equipment is more like $1,000, $2,000, and we are like about $500 for the complete box with all accessories. And we are really innovating in the field of open source hardware. We are actually one of the first commercially available on the DIP devices, which has an open source CPU design inside. So instead of having a OMAP chip, which is a microchip which has been engraved, which is fixed, and which is proprietary, we don't know anything about how the OMAP chip works in the BeagleBoard, for example. We have an FPGA. An FPGA is just a blank plate of reconfigurable silicon. It's like a CDRW. You can program them over and over again as many times as you want with your own CPU design. And that's what I did for the milkymist. So the FPGA implements what is called the milkymist system on chip, which contains the CPU, some I/O interfaces, and accelerators for the compute-intensive parts of the video processing. And so basically that's just a computer. It's more or less like a BeagleBoard. And on top of that, I have my own video synthesis software called Flicker Noise, which runs on the system on chip. So what do we have on the board and in the system on chip? We have a video input for filming the performers. We have VGA output to connect to beamers and other projection devices. We have DMX. DMX is a protocol for controlling stage light, so that's something which is definitely for stage people, because with DMX they can synchronize the light ambience of the room with what is being projected on the screen. They have MIDI. MIDI is a protocol for music keyboards, for controllers. Actually, people can get really creative with MIDI connecting controllers. The MIDI can also be used to talk to Arduino boards, because one of the good points about Arduino is people get really creative inventing new shields, new interfaces, new sensors, and you could just use Arduino in conjunction with the milkymist one device to interact with as many sensors as you want into the visual performance. You can synchronize with the sound very easily because it has line audio and built-in microphone. So you just throw it in some concert and it will automatically synchronize to the beat of the music or this type of thing. It has Ethernet connectivity basically for the updates. So it has automatic download of updates and patches. Well, the patch are what is called the visual effects in the device, little snippets of code. It has open sound control as well over the Ethernet. We are planning on implementing also some video streaming, video encoding and streaming into the device, but that's more something which is a bit experimental and it's not really working now. Actually, it's not working at all. It has infrared for remote and USB for user interface. Because one of the nice things about the thing is that it's completely autonomous. You don't need a computer to operate it. Now, what's inside the chip of the device? Well, the chip is based on the Lattice MICO32 CPU. So that's a RISC CPU, 32 bits. It's very similar to ARM7, but it's open source. Actually, it's made by Lattice Semiconductors, as you could guess. But Lattice has been very permissive about the licensing of the CPU design, and they released it under a BSD-like license. So we just took the code from Lattice and integrated into the milkymist system. We also have our own DDR SDRAM controller. That's actually something which seems innocent, but it's actually a lot of work to get the DRAM to work. It took me, the first year of the project basically was about making the SDRAM to work on the device. Well, I didn't have a lot of experience with FPGA design at that time, so if I were to do it now, it would take less time. But when you are beginner with FPGA and you start with a DDR SDRAM controller, it can get really hard. And that's actually why most open source projects don't have any working DRAM on the boards. We have all the I/O peripherals for the milkymist one, everything that I explained, the DMX, the MIDI, everything is integrated to the same chip. And that's actually cool because it enables me to reduce cost. So by having this custom chip, I can also absorb some of the cost of the FPGA by just integrating all the extra feature, all the very special I/Os into the same chip. It also has some texturing acceleration. So if you have heard of OpenGL, it's just texture mapping, but in 2D. It has some vertex floating point acceleration. It's like a vertex shader in OpenGL. That's also here to accelerate the speed of the processing during the video. So that's also pretty nice features that I can have using the FPGA approach, is that I can get a lot of performance. Actually, I could get them as well from the OMAP, but then I would have to use proprietary blobs, in fact. So on top of that, we run our own software called Flicker Noise. And Flicker Noise is really trying to focus on both flexibility and ease of use. The effects, the video effects which are in the device are not really built in Flicker Noise. There is a predefined framework, but most of the appearance of the effect is built into a little snippet of code that you could create on the device itself. And we call such snippets of code a patch. It's similar to, for example, a pure data patch or a maxMSP patch that people might already be familiar with. So we have our own domain-specific language for doing this. It's called the Flicker Noise patching language. It's inspired by milkdrop, which is an audio visualizer plugin for Winamp. And we found this language pretty nice to implement with hardware acceleration. And we found it was quite extendable and not too complicated to do either. So we just took this language as a base, implemented more features to put some features that were hard to implement, and this becomes a Flicker Noise patching language. Actually, it retains quite some compatibility with milkdrop, and when I'm going to do the demonstration later, you will see most of the effects might remind you of something if you have used milkdrop before. For creating this, we have the graphical user interface built into the device itself. So you don't even need a computer. You can just be on the go, just take this little box here, and you are set to create any kind of effect you want. And for people who are not programmers at all, for the people who using the Flicker Noise patching language is already very difficult, you can just connect the whole box to internet, and it will download patches from a shared pool of users. And you can also send us your patches that you create, and the device will download them. That's actually how the Flicker Noise user interface looks like. So this is a screenshot of what is running on the device. You can see it has some normal file system. This is a Flicker Noise patching language editor. That's another screenshot. You can see here the online help system. It's actually a PDF reader. We have PDF help on the device. Well, we don't really need PDF, in fact, but it was just to test the capabilities of the system. This PDF reader demonstrates, we did it more for the fun than for actual use. We did it just because we can. We just took the new PDF source, we took the free type source, libpng source, all the libraries that new PDF depends on. We just compile everything for the Lattice MICO32 architecture and for the real-time operating system that we use. And we got it running on the device very easily, in fact. So that demonstrates the capabilities to run existing software into such a device which might look weird at the first place. We actually have a lot of other traditional software running on it, like Ruby, Lua, Linux. Well, basically, just any POSIX software should work on the device. That's one of the effects you can make with it. So that's actually my hand, which is hanging like it, and the device makes some effect by running some patch. Another effect here. You will see it later more during the demonstration. I'm just putting some still shots here, just to give you a preview. So, now one question. Why should I make such a device open source hardware? I mean, I have a very clear set perspective of how to make the product. Now, why make it open source? Well, I could give some philosophical reasons, but I will just explain what open source hardware has done for this device, because we got quite a bit of contributions. And the first one, which was very interesting, was a JTAG debugger board for the device. So you can see here the main board of our milkymist system. And this little board here was a contribution by someone who wanted to replace the proprietary Xilinx flashing cable. And instead of having this big cable, which costs a lot, we have this little FTDI chip breakout board, which connects to USB, plugs on the milkymist board, and you have JTAG and serial in this little handy device. So that was one of the first hardware contributions that we got. It was really cool. People are porting Linux on the device. So you can see here our very first development board. In fact, that's not our board. It's an FPGA board from Xilinx. And we were using Xilinx boards at the beginning of the project before we had our own PCB. And that's a Linux test. It dates from September 2009, actually, I think. You know that. We have now, more than Linux, we have OpenWRT distribution support. It has taken a long time. Actually, OpenWRT is pretty new. That's because the initial Linux port has tons and tons of problems. It has problems with the libc executable loader. It had problems with drivers, with stability, with context switches. It was basically a big mess. The photos that you've seen before is a bit misleading because you have the impression that it works really nice with the frame buffer. But the average lifespan of the system was something like 1 minute or 30 seconds before it crashed. You had no shared libraries, you had memory leaks everywhere. Well, it was really a mess, and the code was horrible otherwise. It was basically a demonstration. But now we have people who have worked on that, and we have a pretty nice Linux port, which probably will be merged upstream in a couple of weeks, I guess. And thanks to this very clean Linux port, now we have the support from the OpenWRT distribution. I spoke about the compiler as well. GCC gave us problems with Linux as well. GCC is difficult and hard to fix when it breaks. And now we also have people working on LLVM. Actually, they didn't start working on LLVM because they wanted to work on milkymist, but they started because they wanted to create a computer architecture company which would dynamically add instructions to the CPU. And they found that GCC was a bit messy and not very nice to play with. So they took LLVM as a base, and they found that milkymist was a pretty nice platform to use. So they just started porting LLVM to the LM32 architecture that we use. So the status is still pretty experimental. We can compile on Hello World since probably last week or something. But first results are very encouraging. And hopefully we will compile the full software stack with LLVM at some point. We are not using Linux. I just shown Linux before, but we are not using it on the device that we produce. Instead of that, we use a lighter operating system called RTEMS. It was actually an operating system created by the US Army in the late 80s. And the advantage over Linux, it's much lighter, it's easier to port, and it's still POSIX compliant. So it's not difficult to compile libraries and compile existing software to RTEMS. You basically the biggest source of problem when you are taking a piece of software written for Linux and you try to run it on RTMS or milkymist is the GNU AutoTools system. This system, I will not talk too much about it because you might not like what I'm going to say, but well, that's the biggest source of problems when you are porting something. And for programs which use a normal makefile, it's just basically just changing the compiler, setting a couple of flags, and you get your library or Linux, typical Linux software running on RTMS on Linux. So that's a pretty nice operating system. And it was ported in part during the Google Summer of Code 2010. And that's what we use on the device now. Another very nice contribution was an on-chip GDB server. thanks to the reconfigurable approach that we have with the FPGA, you can make any kind of modification you want to the CPU design. You can implement whatever feature you want. And someone made a GDB server. So the chip actually speaks the GDB protocol. You just have to connect a serial cable to it. You just use GDB remote, and you are all set to get stack traces, to set breakpoints, to use single stepping, to evaluate variables when the program is running. Basically, you have all the facilities that GDB provides, but just on the remote device. So it makes debugging a lot easier now. It's just as if we were running software on our local PC. We have QEMU emulation support. So you can just run software for milkymist just by using QEMU. So I will just demonstrate it now. So you just run it with QEMU system. Okay, it's loading now. Well, now it takes a little bit of boot because of the DHCP client, which is hopelessly trying to send the network to QEMU, which is not responding. And the user interface will probably appear in a few moments. Yeah, now it is. So that's actually the Flickr software, which is running on my PC now, instead of the device. And with QEMU, you can do anything you want. You can just use GDB, you can get dumps, you can get traces of execution, well, anything you want. And everything works. I mean, you can even start the rendering of the patches into QEMU, and it will use OpenGL to accelerate the treatments that the software is requesting from the hardware. So that was a very good contribution. And it is merged into QEMU 0.15, which was released a bit very recently. The problem is that distribution maintainers still do not build for the LM32 architecture. So if there are any distribution maintainers in this room, please build the LM32 target architecture for QEMU system. This will make our life much easier. Thank you. We also had a little bit of collaborative hardware debugging. What you see here is the video chip that we had on the very first prototype. And this video chip has an output pixel port, which sends the digitized video to the FPGA. But we were out of luck on this third version because the port can be set in 16 bits, and it can be set in 8-bit mode. And the FPGA uses it in 8-bit mode. And when it's in 8-bit mode on a 16-bit port, you could either use the upper bits or the lower bits, and we used the wrong one. So the FPGA, the video chip was happily sending bits using its not connected pin, and of course the FPGA was not receiving any video. So it was a bit of fixing. We had 16 pins to connect correctly to this chip. 3 people tried, including me, and 2 people failed, including me, and only one managed to do it. It was not someone which had any contact with us. It's just someone that we sent a couple of prototype boards around to some people who were interested in them, and he just fixed his board. He was pretty good at soldering. And thanks to this guy, we knew that we just had to fix these bits on the pixel port to get the video input to work. So on the next version, we just connected them correctly, and it was working pretty flawlessly. That was some other collaborative debugging that was made over IRC. So we just, actually, debugging hardware on IRC can be challenging. Sometimes you have to make drawings, you have to send emails around with schematics, and well. But it works pretty well, in fact. The case design also was made by people involved in the open source movement. It was made by a little hackerspace called Raumfahrtagentur in Berlin. They have a laser cutter, and that's one of the first version of the case you see. The first prototype was made out of acrylic, of plywood, sorry. And now we are just reusing the same design, but using acrylic, which looks nicer. So that's the result here. You will see it later. So manufacturing was is made by people who are from OpenMoko originally. OpenMoko is more or less dismantled now, but people from another company called Key Hardware, and they take care of the complete manufacturing and of the milkymist systems. And you can see here some solder checks, because the device uses a BGA chip. So BGA is like a grid of pins. The particular BGA chip that we use has 484 pins on this size. and it's a grid. It's a grid of solder balls. So when you are soldering this, you have no access to the solder which are under the device. So you need to heat the whole thing with a reflow oven, and then you don't see anything actually happening. You just have to use the correct temperature profile and hope that everything went okay. But how do you check? Well, that's one of the checks that we did. It involves X-raying the board. So just it's like a radio, like you go to the dentist, but here with the board, and you can check that all the solders that you cannot see with visible light are actually okay. So we even have some very interesting uses as well of the milkymist developed source code for scientific research. One of the first reuses of this technology, which is, I find pretty impressive, was the reuse of the DDR SDRAM controller that I wrote for the device for a software-defined radio experiment of the NASA. It's called Connect. So it's an experiment which explores the use of software-defined radio for telemetry purposes and so on. And it's going to be launched in next January, and put on board the AISS. And it's using the SDRAM controller from milkymist. So that's a pretty interesting achievement. And another pretty good use of this stuff is the particle accelerator control system at GSI and CERN are reusing parts of the modified lattice MECO 32 port core that we did for milkymist. Like, for example, they are using the GDB server or chip GDB server, etc., to control their stuff. And it's pretty interesting because these two accelerators have a very open policy regarding licenses. And they even have opened an open source hardware repository where you can find a lot of designs from these facilities. It's ohwr.org, and you can download basically a lot of FPGA source code or hardware design which are used to run the LHC and GSI. So if you go there, you will even find the modified M32 core, you will find control boards for particle accelerator, and everything is in open or license. That's a very good initiative, I think. And hopefully, at the next presentation, I will be able to present something that you did, hopefully. For this to happen, you are welcome to our IRC channel. You can send to our mailing list, follow us on Twitter, fork us on GitHub. Well, we are on open source, so go ahead now. Before the demonstration, do you have any questions? Sorry, can you speak a bit louder, please? Use the mic.
Hello? Okay.
Yes.
I have a question about which FPGA are you using and which clock speeds can you reach for both the CPU and the DRAM clock?
So the CPU is a Spartan 6 LX45. So that's not a very big FPGA. And the CPU is running at 80 megahertz now. You can push it to 90, but I haven't really tried to optimize that. And the SDRAM is running synchronously with the system. So that's also 80 megahertz for the SDRAM. And because we are not using any clock domain transfer between SDRAM and CPU to reduce the latency, actually you can download the architecture report from milkymist.org, and it will explain all these features of the DRAM controller and why we are not using any clock domain transfer. So, and actually, we might even try, in some later version of the system on chip, is to double the SDRAM clock. So the SDRAM will go to 160 megahertz, still with the same FPGA, in order to get more memory boundaries and higher resolutions and pixel depths.
Okay. Thanks.
Other questions? Yep.
I'm just curious, when you're launching this into space, and I apologize if you mentioned this, what have you done to harden it against radiation? Is it just the case, or have you done additional, error handling, this type of thing?
I didn't do anything personally, but when the NASA took my source code, they used trip modular redundancy. So this consists in using 3 flip-flops instead of 1 for each register in the FPGA. And at the output of these 3 flip-flops, you have a voter circuit, and the voter circuit will determine the majority of the outputs of the flip-flop. So if the two flip-flops are 1, 1, 0, it will output 1 and assume that the flip-flop which put out 0 was in error. If it's 0, 0, 1, it will output 0 instead of 1 and consider that 1 is in error. And so they use triple modular redundancy, and they also use what is called a scrubbing engine. A scrubbing engine is an FPGA core which reads the DRAM all the time, uses an error correcting code to check for errors, correct the errors, and write back the data if there are any error. So this thing is running continuously to check for errors which have happened into the DRAM core.
Yeah, so basically software redundancy.
Yeah, they're using software redundancy. It's hardware redundancy because the scrubbing engine is running in the FPGA. It's not a piece of software. It's a big FPGA stat machine, which does that all the time. And it's the same for the flip-flop. The flip-flop are inside the FPGA.
Yeah, and what is the life cycle, the duty cycle for the space station? Is there a amount of time that it's supposed to be in service there?
What is what? Sorry?
You said that it's going on the International Space Station.
Yes, yes.
How long will it be there? Or how long is it anticipated to be operational on the International Space Station?
I don't actually know, but I can ask if you're interested in this.
Okay, yeah, it's very, very curious. Thank you. Very nice.
I have one question about actually, it is open source hardware, so all the source code, the VACL, I assume, is available?
Yes, if you go to milkymist.org, you can download the complete source code for the system.
Then if you want to synthesize it for your own FPGA, you're still dependent on the synthesis tools from Xilinx.
Right now we do, but we are working on alternative tools for the Xilinx FPGAs. I don't know if we are going to continue on that. We already have some results. We can synthesize very simple designs, but I don't know if we are going to continue on this tool because they don't generate a lot of interest, unfortunately.
Yeah, because the open source synthesis tools, they are not really, they're not really there yet. I mean, it's not the same quality as, for example, GCC.
Well, right now we are using the software tools on the FPGA vendor, which are proprietary. So you have to download them from Xilinx. It's a big blob of software. Well, it has a couple of bugs, of course. It has some problems, but personally I can live with them.
I have one more question. It's about how does you picked a MIPS CPU?
It's not MIPS, it's Lattice Mico32. Actually, Lattice Mico32 is not very different from MIPS, but it's just available, it's good quality, and it has an open license. So that's why that's the criteria we used to choose this CPU.
Okay. There's also another open source CPU available from Geisler, the Leon CPU.
Yeah, there is a Leon CPU from Geisler. It's a Spark CPU, and we did not use it because it's big. I mean, it's a good design, it's well documented, it's very professional, but the problem is it uses lots and lots and lots of FPGA resources. That's the reason why I didn't use it. Lattice Mico32 is a very light CPU and very efficient.
Okay, thank you.
So if there are no more questions, I think we can switch to a little demonstration now. Unless someone has, oh, yeah. Please come to the mic. Yeah? No? Okay. Okay, so let's demonstrate the device now. It's already started. I just switch it from the switch the beamer to it. Yeah, that's our user interface. That's the device now. And here's the camera. So I will film you a little bit. Well, don't see a lot of things. Let me just touch this. And now I will load some effects, so that's the patch editor. And I'm going to load some effect written in the flicker noise patching language. That's the image of the room, of the cables here, actually. And you can make such a demo with, I will put a bit more light. And this effect is only made with 7 lines of code. That's actually what you can do with the FNG language. If I load some other effect now, it's a bit similar, but what you can get. Actually, the contrast of the camera is not very good because I get all the light from the outside. But if you make a proper setup with a black background and some lights coming from the front, it's much better. And when you are making a performance with the device, obviously you are not using the user interface on the beamer, so you can map effects to the keyboard. Well, you can do it with the USB keyboard, you can do it with the MIDI keyboard, you can use input from Arduino, you can basically do anything you want. And you just map keys. Here I will just use the USB keyboard to switch between effects. And just, for example, associate the A key to this particular effect here. And define the first patch. So now it's pre-compiling all the effects in order to make switching between them very fast. Because the effects are compiled, the vertex shader inside the milkymist is like a floating point, microprocessor, and the main CPU is reading the click-on-noise matching language and compiling everything for the floating point accelerator, so everything gets executed very fast. There are like 70 million floating points per second done on this small FPGA. And actually, it's only using a very small fraction of the FPGA just to do this 70 million floating point operation per second. And now when I press the keys, I get all the effects mapped. So this one actually works with sound. So when I tap a bit on the box, the internal microphone picks up the sound and makes the effect react. And you can tune the reaction of the effect to the sound just by writing different codes in the click-on-noise matching language editor. That's yet another effect. You can tune the keyboard, for example. This effect was done at a festival, actually. Someone really liked the device and he wrote tons of effects for hours on it. And this one was just made on the go at a festival a couple of weeks ago. It was a PGA festival. What? Yeah.
In the meantime, are there any questions from Flow Control?
Yep.
Do you try connecting the Connect or the Connect RP?
The what?
Microsoft Connect camera.
No, I didn't try, but you can try to do it yourself if you want. It should be possible.
Could be interesting to use the 3D point cloud of the Kinect.
Maybe, yeah. That's what, this idea is coming up all the time, actually. But I never tried. Yes, there is USB host.
We needed a question for the stream. What was your question?
Sorry. Which question? Yeah, the question was about whether it was possible to use the Kinect API or not. So it was, the answer is that this idea is coming up all the time, but no one really tried it yet. And, yeah.
Dear interested guest, would you please use the microphone?
If you want to connect Kinect to your box, then the host controller, controlling USB, should at least support USB 2.0. So it's running at 480 megabits per second, because the Kinect produces raw video of about 80 megabytes per second. So does the PHY on the board support USB 2.0?
No, it does not. So maybe that might be a problem, actually.
Oh, okay.
I never really tried. I mean, I'm not interested in the Kinect at all, so I have no idea how it works.
So are there any more questions left?
Yep.
When is available and how much does it cost?
It will be available in a couple of weeks. Right now we have some development kits, but they are going away, most of them. And in a few weeks we should have the end product for about $500. So that's half the price of some professional video mixing device.
Any more questions? From the internet? No?
From the internet? No.
Thank you, Sebastian.
Yeah, thank you for your attention.